Hi, my name is Manish Gupta, and in this video, I'm going to talk about the newly launched Code Llama models from MetaAI. So what is this Code Llama family of models from MetaAI? Well, it's a family of large language models for code based on Llama 2, which is also something that has come up very recently. It provides awesome capabilities, code infilling capabilities, support for very large input context up to like 100K tokens, and zero-shot instruction following ability for programming tasks. Right, it is trained on, so these models are all trained on 16,000 plus token sequence length, and they actually work well with even 100K tokens at test time. Uh, there are three different sizes of models: 7 billion, 13 billion, and 34 billion. 7 billion and 13 billion Code Llama and the Code Llama Instruct variants also support infilling based on the surrounding context, right? So 7 billion and 13 billion, whether it is Code Llama or Code Llama Instruct, they basically both support infilling, right? In fact, in the family, there are three types of models: Code Llama models, Code Llama Instruct models, and Code Llama Python models. And as you see, they are all derived from the Llama 2 models by following various steps that you see here. So for, there is code training or infilling code training, which is going on 500 billion tokens. Second step, the Code Llama Python models are actually further fine-tuned on Python code, 100 billion tokens of that, and long context fine-tuned on 20 billion tokens. So that gives Code Llama Python models. While on the other hand, what you have is you can ignore the Python code training and then just do long context fine tuning that gives you Code Llama models. And if you further also do instruction fine tuning with 5 billion data, you basically get Code Llama Instruct models. So that's that. So they are in fact a state of the art among open models with scores up to 53% and 55% on large language model benchmarks like HumanEval and MBPP. Right? Code Llama Python 7 billion model, this one actually performs better than Llama 2 70 billion also. So, the large 70 billion models on HumanEval and MBPP both. Uh, Code Llama models are actually better than any other publicly available model on a multilingual benchmark called as multiple. Right, so this is multilingual in the sense it contains other programming languages as well besides Python, like C# and C++ and so on. Okay. So Code Llama Instruct models, these ones are specifically trained, fine-tuned using human instruction data and self-instruct code synthesis data that I'll talk about in the next slide. Infilling models, these models, 7 billion and 13 billion models, which have been represented using this bidirectional sign. These infilling models actually are appropriate to be used in any integrated development environment to complete code in the middle of a file. So you're in the middle of a file, there is some chunks in the beginning, some chunks later. How can you infill, right? So that's that. And the best part, these models are all open. They're released under permissive license. So how are these models trained? Well, they are trained in three different steps, as you see on the previous slide as well. So, infilling step, and then there is long context fine-tuning step, and then instruction fine-tuning step. And that is what I'll talk about in this slide, right? Infilling, long context fine-tuning, and instruction fine-tuning. For pre-training, in fact, this kind of data is used. So Code Llama models have been pre-trained on 500 billion tokens or other infill code trained on 500 billion tokens as here, right? Starting from Llama 2 kind of models. So these 500 billion tokens mostly contain code, 85% code, but they also contain some natural language related to code, like, comments or discussions, question answers around code, and also pure natural language data about 7%, so that they still retain the natural language understanding capabilities. The Code Llama by Python models basically make use of 100 billion additional tokens, and they are essentially trained on 75% part Python, but 10% other kind of code, and then 10% natural language related code and 5% natural language data. Those models which have been trained for infilling task, well, the idea there, the task is basically predicting the missing part of a program given surrounding context. And the way they do that is for 90% with probability of 0.9, they take the training documents and they split it into three parts at character level: prefix, middle part, and the suffix. The positions are randomly decided for splitting. And then they train half of this 90% is trained using the PCM kind of input format, and the other half using SPM input format. So the PSM versus SPM. PSM stands for prefix, suffix, and middle part, and SPM stands for suffix, prefix, and middle part. The idea is to do causal masking in the sense that take a particular middle part and then put it right at the end and use the prefix suffix or suffix prefix kind of combination so as to predict that missing part in a causal way, in an autoregressive manner. Right? So the other part is part of their training pipeline is long context fine tuning, where they essentially fine tune with input sequences of size 16,384 tokens. The way they make this work is by modifying the rotation frequencies of the rope embedding technique, position embeddings, right? And the way they do that specifically is that in rope, essentially you use theta i's, which are like theta raised to minus 2i by d. In their case, they increase the base period theta from 10K to 1 million, 10K to 1 million. And that is how essentially they make the long context fine tuning work nicely. Okay. For instruction fine tuning, they use three kinds of data sets: proprietary data set from Llama 2 called as RLHF v5, which was also discussed in the Llama 2 video that I recorded a few days back. They also use self-instruct data and rehearsal data. So self-instruct data is created in a very interesting manner. So the first step, and self-instruct data basically contains around 14K questions, tests, solutions, triplets. Okay. So the way this is created is first you essentially ask Llama to 70 billion model, you prompt it appropriately so as to generate 52,000 interview style programming questions. You take these programming questions and you ask the Code Llama 7 billion model to generate unit tests. And then you also ask a Code Llama 7 billion model to generate 10 Python solutions for each of those unit tests, right? Now, once that is done, you compute the pass at k metric, or rather, you basically try to look at all of these 10 Python solutions and pick the first one that passes the unit test that was designed here, right? So that finally ends up in giving around 14K question, test, and solution triplets, which are what are also used as part of the instruction fine-tuning data here as self-instruct data, right? The last one is rehearsal data, and the idea there is to avoid any regressions, and therefore they basically also leverage code data set 6% and natural language data set 2%, just like they were also used here for Code Llama Python and also for Code Llama kind of data set. Yeah, Code Llama, a data set used to fine-tune Code Llama models. So how do Code Llama models perform? Well, they do several experiments to check out how good they perform well on several data sets, and so HumanEval, MBPP, and also other data sets which are mentioned in the paper. They compare with the state-of-the-art code-based large language models like Palm Coder as well, right? They also compare with Llama 2, right? And they compare on pass at k metric. Pass at k metric basically means that if you take k of different outputs generated by this model, so if you just took one, or rather if you took k, then what is the probability that at least one of them passes the unit tests, right? So what you find here is that if you look at Code Llama models, they are typically way better compared to the equivalently sized Llama 2 models. If you look at, and therefore, if you in fact really look at the 70 billion Llama 2 model, that gives you these kinds of values, which are very equivalent to Code Llama 7 billion model. So Code Llama 7 billion model is actually almost equivalent to Llama 2 70 billion model. Okay, that's that in terms of performance across both the data sets, right? Also, what is observed is that if you look at Code Llama Python models and compare them with the Code Llama models, typically you will see that these models typically perform better compared to the Code Llama models. Right? So that's that. In fact, Code Llama's Python 7 billion is actually better than Code Llama 13 billion, larger sized model anyway. Right? So even when you look at multilingual benchmarks, so they took the HumanEval benchmark and they've created something called as multiple benchmark. So multiple benchmark which basically has languages like C++, Java, PHP, C# and so on. And what they observe even with the multiple benchmark is that Code Llama 34 billion gives you really awesome state-of-the-art results on this benchmark compared to any of the existing awesome coding models, including Codex and Star Coder and so on. Okay. Now, further, if you basically look at a single line infilling kind of task, so if you basically just hide one line and ask it to regenerate that line, and you match and you basically try to evaluate how good it does on exact match. Exact match basically means it must be able to recover that line exactly as is. You actually find that Code Llama model 7 billion, 13 billion. Remember the larger Code Llama model was not trained using for infilling tasks. So if you look at the 13 billion model, that actually outperforms the existing best code LLMs in terms of single line infilling as well. Okay, so here are some examples of standard Python bugs found and explained by Code Llama Instruct. So you can actually give it a prompt like this. This function has a bug, and then essentially, you can actually explain that currently, if you call this model with some input, it returns some output, whereas it should return this. What is the problem? And then, it can actually explain very nicely. You are correct. The function indexer has a bug, and then it can actually tell you what is the exact bug, and it can correct the function for you and then tell you, okay, it is the bug-free code. Okay. It can also solve complex tasks. So you can actually give prompts and explain, you can give prompts explanations for a domain-specific task, and then you can expect it to be able to answer that accurately. So this is an example in Bash. How do I list all text files in the current directory, excluding subdirectories that have been modified in the last 1 month? Now, this is a very interesting command, and a difficult to come by, difficult to get to command, right? But it does it so nicely and also explains the meaning of each of those. I personally used some such models also for, trying to figure out the appropriate parameters for FFmpeg. FFmpeg is pretty complex to use. I mean, if you really want to use it for very niche use cases, right? Similarly, you could actually ask it to do more complex tasks, like, can you please write a terminal command which trims the first 3 seconds of an audio file, adds reverb to the trimmed file. Right? So it can actually come up with nice explanations as well as appropriate commands with the right parameters to be run so as to achieve the task. Here is an infilling example. So these are examples of docstrings which are generated using the Code-Llama models. This is one example. This is yet another example. This is yet another example to show how it can actually generate very large docstrings also. So of course, the full code is not shown here, but the full code was pretty long, but it was able to very nicely explain not just the type of the input, but also what is the semantic meaning of the input that is being that should be passed on to this function and basically creates a very awesome docstring. So in summary, in this video, I talked about Code-Llama models. They are code-specialized Llama 2 models, 7 billion, 13 billion, and 34 billion in size. And in fact, the family contains 3 kinds of models: Code-Llama, Code-Llama Python, and Code-Llama Instruct. 7 billion and 13 billion checkpoints are actually also trained to support infilling tasks. All models actually leverage very large context. They've been trained using 16,000 plus context sizes, and they work well with up to 100K tokens. 30 billion model is state of the art among public models on standard Python completion benchmarks like HumanEval and MBPP. On multilingual benchmark called multiple, even the smallest Code-Llama model, which is Code-Llama 7 billion, is better than all other public models. OK, so that's it. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage.